and what the 9 regions delineated within the abdominal cavity. Just draw a tic-tac-toe board. That's what we do on the abdominal cavity, and we number these sections 1, 2, 3, 4, 5, 6, 7, 8, 9, and they all have fancy names. It just goes right hypogastric, epigastric, left hypogastric over here, and then right lumbar, umbilical in the middle, left lumbar, finally right iliac, hypogastric here, and left iliac. Notice that I was using this person's right and left, not my own. That's key when you study anatomy and physiology. Whenever you use right and left terms, you're talking about this person's right and left, not your right and left as you face them. All right, that finishes chapter 1. I'm going to talk about chapter 2 is a bit, in my opinion, it's a bit more complicated than we need to get. So I'm never going to ask you anything on an exam. Let me get rid of this board. I'm never going to ask you anything on an exam that is not in your textbook. It's all in there, but there's so much in there that I can't ask you everything that's in the textbook. So that's sort of what these talks are about. It's to help you know where to focus, what sections to focus on. That's also why I put up an outline on the Canvas course page for every week's module, is to help you focus your studies. Doesn't mean don't read the book. It means focus particularly on the sections that I put on the outline. Also, these meetings, I can't possibly go through every single detail, even within those sections, but I can try to help you make them easier to understand. And it's not more true than this, I think it's called Chemistry Comes Alive, which is kind of a cheesy title in my opinion, but this is not a chemistry class and it's not a biochemistry class. So I'm going to tell you right now, and I've written it on the outline, what sections you need to focus on. And really quickly, I'm going to call up another whiteboard. First, we just need to know that atoms make up molecules and they combine to form structural building blocks of living things. So atoms, things like carbon, oxygen, nitrogen, hydrogen, those are atoms. They make up molecules, like molecules of water, for example, and those things combine to form the structural building blocks of all living things. So I do want you to know this business. Types of, so I'm distilling chapter 2 for you, or with you. Types of chemical bonds. And there's 3 types. I'm going to list them and say a few things about them. It's all in your book, but I'm going to help you. First, number 1, ionic bonds. These are chemical bonds between atoms that are formed by the transfer of electrons from one, the key word is transfer of electrons. That's how they are formed, from one atom to another. And when there's a transfer, one molecule becomes negatively charged and the other one positive, and then the attraction between the two creates a bond. So a classic example that all books give, sodium chloride, that's simple table salt. How this bond of sodium chloride exists is that the sodium transfers an electron, which is negatively charged, to chlorine, so that when the sodium ion loses an electron, it becomes positive, and it gives its electron to chlorine, which becomes negative, and this attraction creates a bond between these two molecules. Second type, I think I'm going in the order of your book. I don't have my book open anymore. Covalent bonds. These are formed when electrons between atoms are shared, not transferred. So I'm going to write sharing of electrons. These are the strongest type of individual bonds. Okay? So one pair of electrons gets shared between two atoms. If a hydrogen shares electrons with another hydrogen, that's called a single covalent bond. If an oxygen shares electrons with another oxygen, we put two hashes there, that would be a double covalent bond. And finally, nitrogen to nitrogen is a triple covalent bond. These are very strong in nature. Finally, number 3, hydrogen bonds. This is the third type. These are attractions between slightly positive side of a molecule attracted to a slightly negative side of a whole other molecule. The classic example is water. So I'm going to quickly draw a water molecule. And it's easy to draw a water molecule. You just draw a Mickey Mouse head like this, where this is the oxygen and these are the two hydrogens. So this is water. Now, that's a molecule. It's not an atom. It's made up of an oxygen atom and two hydrogen atoms, but that's a water molecule. And in nature, the oxygen side of the water molecule is negative, and the hydrogen side of the molecule is positive. And because of that, it attracts, guess what, other water molecules. So the oxygen part of another water molecule is attracted to the negative part right here. That's a hydrogen bond. So here's another water molecule being attracted, the second one being attracted to the first. We call these hydrogen bonds. These are very weak individually, but they become very strong when they multiply over millions and millions of these bonds. Very strong. I'm going to put when many. That's how water can hold together, water molecules. If you spill a little bit of water on the floor, it puddles, it holds together. All the water individual molecules don't spray apart. It's these hydrogen bonds that are holding water together. All right, that's it on those bonds. Now I'm going to quickly talk about, this is what you need to focus on from chapter 2, acids and bases. So the definition of an acid basically is anything or a substance that releases hydrogen ions, gives off, they're called protons or hydrogen ion. These things create an acidic environment. So anytime in the human body that you see free hydrogen ions, it's an acidic environment, all right? So an example, classic example, hydrochloric acid, which your stomach secretes, by the way, that's HCl. That's hydrochloric acid. When it hydrolyzes or mixes with water, it breaks apart, and it gives off hydrogen molecules, protons, and bicarbonate ions. This creates an acidic environment. HCO3 negative is just the result. We know water is H2O. When HCl and H2O combine, it breaks off this hydrogen ion, creating an acidic environment. And then it also forms a bicarbonate. This acid, to, these are examples I think that your book gives, which is why I'm sticking to these examples. I'm going to write carbonic acid. It's an acid, it's a weak acid. It's much weaker than hydrochloric acid up here, but it's still an acid. It can break apart in the human body to release hydrogen ions and bicarbonate ions. Sorry, that is supposed to be down here. I got ahead of myself. Still early in the morning for me too. I know it probably is for you. So hydrogen ions plus bicarbonate ions, HCO3. I know I'm confusing you. Let me erase this. That should have been, I was already thinking about buffer systems. Carbonic acid can break apart to also release hydrogen. The key theme of this talk is anytime you see a hydrogen proton by itself, that means acid. All right? This term base is defined as anything that accepts a hydrogen ion. So a base is anything that will grab this free hydrogen ion and bind to it to reduce the acidity. This thing that I've drawn now several times, once by mistake and once correctly, HCO3 negative, this is a base. And the reason it's a base is because it will combine with hydrogen ions to form H2CO3. So we call this bicarbonate ion a base because it will bind to or accept the hydrogen ion. And finally, the term buffer. That refers to something that can change the pH, try to help neutralize extremes in pH. So a buffer in the human body, example would be that carbonic acid, and I'll explain to you why, which is H2CO3. This weak acid is considered a buffer because it can break apart and give off free hydrogen ions to make an environment more acidic. It can also produce this bicarbonate ion, which will accept free hydrogen ion. So technically, in this situation, the reason we call carbonic acid a buffer is because it can break apart to make an environment slightly more acidic, or it can break apart to produce these things to grab all sorts of free hydrogen ions away from the environment. That's a really quick, so a buffer can regulate pH by either donating hydrogen ions to the environment or accepting hydrogen ions to make it less acidic. So I'm sure you've heard the term pH, which is just a measurement. pH is a measurement of acid base in a particular environment. And the lower the pH number, that means it's more acidic. It sounds backwards. So neutral is 7.0. Most of the body's environments are close to neutral. It's not perfect, but they're close. The pH of the internal environments of most places in the human body are close to 7.0. Things like the stomach during digestion would be a dramatic exception to that rule. But by and large, our fluids are close to 7.0 and neutral. If the number gets less than 7, the environment is acidic. So a pH of 3.0 or 2.0 is very acidic. or sorry, an increase in the pH number equals basic or alkaline. So 8.0, 9.0, 12.0, or any variation of those are getting more basic or alkaline. This is basic chemistry that I want to review with you because it will apply when we start talking about certain environments. Finally, this is the last thing I'm going to do before I shut it off today. This is still in chapter 2. And this is where I will pick up with tomorrow's live Zoom meeting. Organic compounds. I'm going to put a star next to this because I'm going to ask you focus on these things in chapter 2. Focus on the types of chemical bonds. Briefly focus on acid base, what they mean, what pH means, and then spend most of your time in chapter 2 learning about the 4 types of organic compounds. So there's 4 main organic compounds in the human body. Carbohydrates are the first of the 4 that your book, I think I'm going in the correct order of your book. Carbs just mean things like sugars and starches. You probably know this. And I want you to read and remember first what are the basic building blocks of each of these organic compounds. So the building block of carbohydrates are monosaccharides. That's supposed to be monosaccharides, monosaccharides, or what we call simple sugars. Classic example is glucose and fructose. Those are simple sugars, and they are the building blocks of carbohydrates. So a starch, like you eat some pasta that's considered a starch, that's basically just a super long chain of these monosaccharides that are hooked up together. It's just a long chain of monosaccharides. So we use those terms. Mono means 1. A disaccharide would be 2 of these put together. This is just language. It's not hard to understand. So a disaccharide is 2 of these sugars, and then polysaccharide just means many of them. And most of the things that we ingest or that are organic compounds are polysaccharides, and it just means many, many, many monosaccharides linked together. This is an example of a carbohydrate, and it's just a long chain of monosaccharides. The last thing I'm going to say about carbs, they produce the easiest, most readily source of fuel for the human body. We break carbs down really quickly. It's very easy for our system to use that as for energy or an immediate source of fuel. Doesn't mean we can't use other things like proteins and lipids and fats. It's just harder. It's a longer process for our body to do that. That's why it's so hard, so difficult to get rid of fat that we've stored on the human body. Also, this word, glycogen. I'll use it. You'll hear it all through A&P 1 and A&P 2. This is how your body stores glucose. So we eat something like a candy bar. It gets broken down by our digestive system, or pasta, if you like to eat pasta. That gets broken down before we absorb it. Then our body absorbs these monosaccharides, glucose, And let's just say we eat more sugar or carbs than we need to use at that moment. We can store the excess monosaccharides in the form of glycogen. And that happens in our muscles and in our liver. So glycogen is just a stored form of glucose. That was supposed to be a D, stored glucose. All right, let's move on to lipids. I'm trying to go through quickly because I know you want to leave. Let's just do lipids, and then I'll start with proteins and nucleic acids tomorrow. So lipids, most of you know that these are fats. They are insoluble in water. You know that oil and water don't mix, or oil and fat don't mix. So they're the opposite of water soluble. They are made up of carbon, hydrogen, and oxygen, but lesser amount of oxygen than carbon and hydrogen. So building blocks of lipids, we use the term, instead of saccharide, we use the term glyceride. So the building blocks are monoglycerides. That's supposed to be CR. Sorry, it's hard for me to get this plastic pencil to work. Glycerides. And so if you see an example like triglyceride, that word just means there are 3 building blocks or glycerides hooked together. So that's just an example. Triglycerides means 3 of those linked together. These act, this is a great form of stored energy. The reason is because we can store it for so long. And part of that reason is because it's difficult. It's more of a chemical process to break down. So we use lipids to do all sorts of things in the human body. But triglycerides are an example. I'm going to give you some examples of lipids or fats. Another example would be phospholipids. That just means a lipid, a fat with phosphates attached to them. It's just a diglyceride really in a phospho group or a phosphate. These are found in cellular membranes. And a third classic example of lipids would be something like steroids. Our body makes steroids. Yeah, you can ingest steroids, but our body makes steroids in the form of a hormone, and these are derived or made from cholesterol. So these are just 3 quick examples of different types of lipids. Triglycerides, phospholipids, steroids. Let's just do, sorry, your book mentions this one, so eicosanoids, or some people say eicosanoid. I learned to say it eicosanoid. Probably never heard this term before. These are mostly prostaglandins, which just means a class of chemicals, chemical messengers that help regulate or mediate in the inflammatory process. They help regulate inflammation. So there's some common types of lipids in the human body, which is the second type. I would recommend, before I completely cut you off here, I would recommend reading ahead on So we've done carbs, lipids. I'll start with proteins and nucleic acids tomorrow before I go into ATP in chapter 3. I like to cut these meetings off at about an hour if they go that long, because I know that it's a lot to digest for your mind. But let me get rid of this and say a few things before we leave. So just before I stop this recording, I have to say this because it's the first day. This is a 5-week course. We are doing a 16-week course in 5 weeks. That's crazy fast. We all have, it's hard for me to teach this course that quickly. I can imagine it's really difficult from a student's perspective. I get that. My advice to you is, if you can make this, if not your top priority for the next 5 weeks, then almost your top priority, you will do well. If you can devote daily attention to this, you will do well, because it goes so fast. You don't have time. I teach you something and two or 3 days later, you get quizzed on it. So that's the good news, is that you don't have time to forget it. Obviously, the challenge is to stay disciplined and on task. You don't have to show up to these Zoom meetings. I will post the recordings within 24 hours after doing them on the Canvas website. However, I can tell you this, I just taught a 5-week A&P course the first summer term, and the students who showed up regularly to my Zoom meetings seemed to fare the best in terms of grades at the end of the term. That doesn't mean I can sit here and guarantee you that you're going to get a 98% if you show up to these Zoom meetings. All I can tell you is, statistically, the students who were disciplined enough to show up every day, yeah, there were a few students who did well just by watching the recordings because they had work or they had other priorities, and I get that. But regardless of whether you choose to show up to these or you choose to just watch the recordings, the most important thing is daily devotion, daily attention. If you don't do that, it will be a struggle. It will be a slog for the next 5 weeks because there's so much material. I'm contracted to go over a certain amount of material in order to get you to A&P 2. And then that instructor is contracted to go over and fit in a certain amount of material so that you can get to nursing school, PT school, medical school, dental school, whatever it is you want to do, you're going to be expected to already have learned this stuff. So if you can sort of bite the bullet over the course of the next 5 weeks, it will go really fast. You'll do well. And hopefully the outcome at the end will be pleasant. So I'm going to just cut off my recording. So